Problem 2 is a summary of all the comparison sorts we've seen so far. And so this one is mostly just filling in this chart. I think this would be something that's super helpful to have on cheat sheets and whatnot. But you can go ahead and think for a moment about what should go in all of these entries. And so hopefully you have thought about this just for a moment, and we can start filling in this chart together. So what is the best case time complexity for a selection sort? Well, selection sort works by looking through the whole array, right? And then one at a time, picking the best element off the front. And this means that it's going to take n squared time, because to fill in every single spot in the array, we have to look through the whole array. And I just realized I wrote theta squared. I meant to write theta of n squared. And this is the same as the worst case time complexity, because no matter what happens, we have to look through the whole array to figure out what the smallest element is at any given step. And we have to do this for every single spot. And so no matter what, it takes n squared, best or worst case. Is selection sort stable? No, it's not. But it is in place. Or at least like it can be implemented in place, and I think most common implementations would be. Now, what about insertion sort? Well, insertion sort is actually a little interesting. We talked about this last week a little bit, but what happens if you give insertion sort an array with no inversions? Or in other words, the whole thing's already sorted. Insertion sort works by checking every element and comparing it to the element behind it to see if it needs to be swapped backwards or like moved backwards. And so if everything was sorted, insertion sort is going to look at every element and go, oh, you're not inverted, no need to do anything. You're not inverted, no need to do anything. And so on and so forth. And it goes through the whole array, doing simply one check with its neighbor, seeing that there are no inversions and moving on. This means all it has to do is one pass over the array. So in the case where your list is perfectly sorted or even mostly sorted, we can say we have a best case time complexity of n, or linear. But in the worst case, everything is actually unsorted and we have to move every element all the way back to the front, right? If our list was in reverse sorted order, it's very clear to see how 4 has to move to the front, then 3, then 2, then 1, and we're doing all of these swaps. And so that gives us n squared running time. Is insertion sort stable? Yep. And is it in place? Yes. And I want to emphasize insertion sort is going to be stable as long as you're not swapping things if they're equal, right? So if your list looked like this, let's say, and you had sorted up to here, and you were about to say, okay, do I need to swap this back? Just make sure you don't swap items when they're equal, and you'll achieve stability. Now, what about heap sort? So we can take a moment to think about this one. Now, this is a pretty interesting one. The way heap sort works, again, is by heapifying everything, which we know we can do in linear time. So it's going to take at least n. And then once we have the heap, what we have to do is repeatedly remove largest over and over and over until we've moved everything out of our heap. And then we can say we've sorted everything by adding in the largest, second largest, third largest, etc., and filling in the array from back to front. So that's how heap sort works. And let's take a moment and think about the heap we're actually working with. What is the best and worst case runtime just to remove that element from the heap? Well, the way heap removal works is that we take the top element, we pop it off, and then once we pop this off, we take the element that used to be at the bottom rightmost place it where the old min was, and now we swim it down, right? And so in the very worst case scenario, how far down does this element need to swim? Well, in the worst case, it has to move all the way from the top to the bottom, and the height of our heap is log n. So in the worst case, removing the min takes log n, or sorry, removing the max takes log n. It's also for a min heap, log n to remove the min, but here we're working with a max heap, right? Because it's heap sort. And so removing the max at worst takes log n, and then we have to do this for all n elements. So we can sort of maybe say, like, using that like vague justification, we can say the worst case time complexity is n log n, because there are n elements and removing them could take log n time. But what's the best case for removing an item from a heap? Well, if every single element was equal, then when you pop the bottom rightmost thing up and put it at the top, there's no need to swim it down because the heap property is obeyed. The parent is greater than or equal to all of its children. And so if every single item in the heap was a duplicate, they were all equal, then popping off the heap actually takes constant time, because you just move the bottom item up, then see that it's equal to the things beneath it, and there is no need to continue swimming down. And we do that for all n elements, so it takes n time. And so that's the best and worst case time complexity for heap sort. Now, the other question is it stable? Unfortunately, it is not, right? But it is in place because, you know, we can use the array representation of the heap and then just pop things off and stick them at the end of the array that they were originally in. So this is wonderful. Now we want to talk about merge sort. And so merge sort works by basically splitting your array in half, calling merge sort on those halves, and then zippering them together. And so because we're decreasing our problem size by half every time, the height of our recursive tree is log n, and it takes n work at every layer to merge or zipper all the elements together appropriately. So we have a best case and worst case time complexity of n log n. No matter what the input is, we have to do all of these steps of splitting the array and zippering them together. Nothing changes that. So the best and worst case time complexity are both n log n. Now, is merge sort stable? Yes, it is. Is merge sort in place? Not usually. Most implementations of merge sort are not in place because it's super duper complicated to do it in place. There is definitely a variation of merge sort that is in place, but it is a beast in a bad way. It's so complex. And so for that reason, people don't choose to use it. Now, what about Quicksort with core partitioning? Well, as we just saw in the previous problem, the best case time complexity is n log n, and the worst case time complexity is n squared. Is it stable? No. Is it in place? Mostly. This is an interesting one. So Quicksort, most implementations of it are going to take log n extra space. And if you think about it, it's because we're doing log, like the number of recursive stack frames that we're making is log n. And so it does take some extra memory for us to do. However, most definitions of in place would say that log n still counts, right? It might not be a constant amount of extra space, but it's not linear. It's better than linear. And so most people would consider Quicksort in place, even though it does take some space proportional to the input size. By most definitions, this is sufficient enough to say it's in place. And so that's 2A. The next parts of this problem say, for selection sort, give an example of a list where the order of equivalent items is not preserved. And so basically, we're trying to show the instability of selection sort, right? So you can take a moment to think about this. And again, we know that the way selection sort works is by looking through the whole array, finding the smallest thing, and then swapping it to its correct place. So knowing that a swap is going to occur, why don't we use this to come up with our example? Let's say, for example, we had some item here and we'll call it 3, and then we had another 3, and then we had a 1. And to distinguish, we can maybe make this the orange 3 and this the blue 3. So you can tell the difference. We're sorting just by the number value, but we'll use these different colors so you can see that they end up in a different final order. So this is the current state. But what's going to happen at the first round of selection sort? Well, we're going to find the smallest element is 1, and we're going to look through the whole array, find it, and we'll swap it to its correct place, which means 1 moves here and 3 moves there. And so already we can see we have changed things up, and 3 is no longer in its correct or original relative order, right? Before the green 3 came first, and now the green 3 comes last. And then what happens next, I guess, depends on the specifics of your selection sort. But let's say that if it sees multiple items that are the smallest, so we're looking at the remainder of the array, let's say it keeps the first thing and says that's the min. And so it would go through and say, oh, look at this is the minimum element. So you stay there. And then what's the next minimum element? Oh, it's this one, so you stay there. And then finally this. And so we end up with this result that is displaying the instability of selection sort, right? The green 3 used to be first and now it's last. And that is problem B. For problem C, notice that the worst case runtime in the comparison sorts on an n element array listed above are lower bounded by theta n log n. Can there be a sort that runs faster than n log n in the worst possible case? This is a pretty loaded problem, so you can take a moment and think about this one. And hopefully you have taken a moment to give it your best effort, and now we can go over the answer. So we can get a sort that is faster than n log n if we can avoid using comparisons. So we've talked a little bit today about counting sorts and radix sorts. If that's the case, then yes, you can avoid it. But if you have to do a comparison sort, then you cannot. And the idea behind this is, let's say you have a n element array full of all sorts of different items that you have to compare to find out the order, right? Well, there are n factorial possible permutations, n factorial possible orderings of every single item in that array. And so how many, if we do a single comparison between two elements, A and B, how many of these permutations can we possibly eliminate in the best case? Well, in the very best case, we could eliminate half of the permutations. Just to start with, we know that half of the permutations have A coming before B, right? And then who knows what the other elements look like. And half of the other permutations have B coming before A. Because n squared is all, or n factorial is all possible permutations. And so if we could compare A and B and realize, let's say A is greater than B, now we can knock out every single permutation where the item A comes before the item B. Or in the other case, if let's say item B happened to be greater, then we could knock out all of these, right? And so that's the very best case scenario, which means we're dividing the number of possibilities in half. And so how long will it take until we've narrowed it down to one possibility? Well, if we're dividing in half every time and we want to know how long it takes to reach one, that's going to be log n factorial. This next part is a little bit of a math trick, so I wouldn't expect anyone to know it off the top of their heads, but log of n factorial is in omega of n log n. And so by this logic, we have done a sort of very loose proof that if we need comparisons, it's going to take at least n log n. And so this was not a super mathematically rigorous proof, but it hopefully helps you see some of the logic behind this. And if you're really into this kind of thing, I recommend taking maybe CS70, maybe 170, and you can learn a lot more about this.